Good day, everyone.
Good day, Mr. Abo.
Right. Today we quickly look at the cyclic natural and angle by the same segment and the same sector. I just want to look at tangent and radius. So we're going to look at these two. But first, let's go to a cyclic quadrilateral. A cyclic quadrilateral, it's just basic. The theory behind it says that opposites a cyclic quadrilateral, opposite angles of the cyclic quadrilateral adds up to 180 degrees. That is A plus C gives us 180 degrees. A plus C gives us 180 degrees. While B plus D also gives us 180 degrees. That is what a cyclic quadrilateral talks about. Then, if you want to tell an cyclic quadrilateral, all the vertex of the quadrilateral must touch the circumference. In this sense, you can see it's exactly all the vertex touches the circumference. That's an cyclic quadrilateral. As long as it's a four-sided polygon and all the vertex touches the circumference, then you have an cyclic quadrilateral. But there are cases where you see some things like this. They look very rectangle-like, but you see this part is not touching the circumference. Hence, this is not an cyclic quadrilateral. So the law of a cyclic quadrilateral states A plus C. That means the opposite side adds up to 180. Likewise, this case. Remember, this is something you want to remember. This, for this case, look at this is A, B, C, and D. These two are closely opposite. You understand? You go with each other. So A plus C here. A plus C here will add up to 180 degrees. Then B plus D here. Add up to 180 degrees. I just tried to letter them A, B, C, D. Anybody could choose to letter them any way they think fit. So this is just the basics. We are going to go to examples later on, but this is just the basics for the cyclic quadrilateral. Okay, now we have another theorem that says tangent and radius creates a 90 degree. When a tangent line meets radius, automatically creates a 90 degree. This can also happen for a diameter, but diameter is 2 radius. Remember, where ST is a tangent line, the radius bisecting it automatically creates a 90 degree. That's something we always want to remember. The radius bisecting creates a 90 degree. So if you see a case like this, where you have something like this, you know this angle, if you're giving here as, let's say, 70 degrees, you already know this place is 90 and that's you find here. If this is 90 because it's the radius and tangent line, here is 90, here is 70, you should know what here is. X will automatically be what? 20 degrees. Some of angle in a triangle. So that is what this one talks about. We're going to take further examples. I just want to highlight those theorems. Okay, where A, B is a tangent line, O is the center, you can tell that this is a radius from the center to any point of circumference. Knowing that the radius and tangent line, the point of bisection creates a 90 degree. Hence, this is going to give us a 90 degree. When we have this case of the 90 degree, and we're told that here is 70, what do we do to find here? How to find x? You sum 90 plus 70 plus s equals 180. But if you don't like that, here this is place 90 degrees. The sum of these two must give you 90 as well. So you just say 70 degree plus x equals 90 degree. Because these two must give you 90. To add up with this 90 becomes what? 180. So we just go straight there. We go for that thing. F to be equal 90 degree negative 70 degree. Which is what? 20 degree. In this case, this is our tangent line. We didn't know that this is a 90 degree. Hence, we can go for that with that. So this is okay. This is another theorem I want to look at. Angle at the same segment by the same chord are equal, are always equal. Once they share the same segment and same chord, they are equal. Now look up. This is a chord. A chord divides itself into different segments. Now this code has divided this circle into what? Segment A and segment B. This is the larger segment and this is the smaller segment. Let me make the example from here. If I create any angle going by this point of the chord on this segment, they are all equal. This is where they touch the circumference. If I at this point, if I create an angle here, you can see this point of the chord and this part of the segment, this part of the circle on this segment. Now if here is angle A, let's name it A. Now if I create another angle still on that, it will still be what? A, because this law on the same segment by the same chord, they will even if I put another angle here, to still be what? A, to still be that same value. If I put another angle here, even as low as this space here, it will still be what? A. They all are on the same segment by the same chord. If I create another angle still here, to still be what? A. They will all be equal because they are subtending at the same segment by the same chord. So they will all be what? A. In the same way, if I create another angle here, down here, in this other segment, if I select it be X, if I create another one here, to still be X, why? They are in the other side, the other segment. Any angle from this same segment, they always equal by the same chord. If I create another angle here, to the what? X still. So like that. So the law of that states that once the angle is in the same chord, the same segment, by the same chord, it's equal. You can also look at another example from here. You have something like this. You could create an angle here and it gives you a angle y, You create another one here, you get an angle y still. If you create another one still here, you still get an angle y. If you create another angle through this, you still get an angle what? Y. Because they are by the same segments. So it's something you only want to consider when you're looking at. Because there are some cases where you have conflicting informations. Like you have something like this. I have something like this as well. Now the question is who connects with who in this case? But if you look deep, if you clean this chord here, you can tell that these two, if you name this A, this will be A. Have you seen it? Now if you bring the chord back, if you clean this chord here, you can tell that these two, this angle is B, here will be B. They will be equal. Now, if you put this chord back, if you wish to. Now, should you clean this chord out, you can tell that if you see they have two segments, you will just have something like this. That means if here is C, here is C. That means here will be C and here will be C. In that case. For this one. Now, if you clean, let me go back, let me start from the I didn't use that card. If you clean this chord here, let's go back. So if you clean this one here, you're going to have two segments here and here. And this is what you got. So here will be A and here will be A. That's what we are doing. Now, if you take out, should you take out this chord, you should have an information like this. That's how we got our B. So these two will be equal. If here will be, here also will be. They will be equal to each other. If you take that, you remember, if you don't clean this, you might not really understand it better. So looking at this, you can tell that these two are by the same segment on the same chord. So it's just an easy way of coming around it. If you clean this chord, clean this one, you'll be left with, if you clean this, you'll be left with the chord here. You will have to the chord here, and let's say we have this. So you're going to have this and this, followed by this and this. So if here is D, here is W, here will be W. So this place will be W and here will be W. So we have every information filled up, knowing that they come from the same segment at the same chord, and they give you values. But sometimes you need to claim eliminate some chord so that you can find the rest. You can help yourself find the rest easily. This is what this talks about.